The interaction between both of them can be explained through the function of an electric motor. To build it, we will need 1.5 volts battery, thin copper wire, 3 magnets, preferably medium big, something to use as a support for the battery. In this case, we use moldable foamy. Process. First, we tangle the copper wire on the perimeter of the battery, leaving approximately 3 cm on each side and scrape off the enamel. Thus, we form a small coil. Then, we take a 10 cm cable, cut it in half, and remove the protection from the tips, and stick the tips to the ends of the battery. Finally, we twist the free end of each cable, and there we place the ends of the coil. We approach the magnets, give a push, and the coil should start spinning alone.
To explain this experiment, it is important to note that Maxwell equations are not so much the ones that govern this, but instead the Lorentz force law is the one that explains it. In the equation above, the second term says that there is a charge q moving at a velocity v. Then a magnetic field will put a force on that charge, which is perpendicular to both the direction of the charge and the field. But what does this mean? If an electric current, which in this case this current is provided by the battery, in a wire is a net flow of moving charge and so a magnetic field, and this field is produced by the magnets in the part below, this will put a force on the wire. In this case, the Lorentz force law becomes the Biot-Savart law. And building on this, if the wire is a loop, a magnetic field will put a torque on that loop and cause the loop to spin. And in these foundations, the electric motors are constructed, and that's the reason why they can function and they can spin. So in simple terms, I can say that in the experiment, the wire is rotating because of this electric current and the magnetic field that are acting on it, and so they are causing them to spin, and that's why, well, you can see it moving throughout the video.